Now that we have looked at taking the Laplace transforms and the inverse Laplace transforms, let's look at see how this can be applied to a differential equation. So here we're given a homogeneous differential equation, and it doesn't really necessarily matter that it's homogeneous, but it is because we have 0 on the right side, and we have two initial conditions, an initial condition for our function and an initial condition for our derivative. So just for simplicity on this one, keep in mind that our function is a function of t. Y of t is the same thing as f of t. Y prime of t is the same thing as f prime of t. Y double prime is the same thing as f double prime. So when you're looking in your transforms, if you see an f prime, it means y prime. If you see an f, it means y. But if you see a big F of S, that's capital Y of S. So that's transformed from T into S. So since we have three terms on the left, we're going to transform each of those terms. We're going to transform the second derivative minus twice the transform here plus 5 times the transform here. So let's just write that out. Let's transform Y double prime minus twice the transform of Y prime plus 5 times the transform of Y. And we have to transform the other side. So when we transform a second derivative, if we use our formula, in this case, this is the second derivative. So this is s to the second power, capital F or capital Y of s. So that's transformed into s, minus s to the 1 less power, y of 0, minus s to the 1 less than that power, so no s's, y prime to the 0. So notice we start with the second power of s and we reduce our power of s. So 2, 1, and no s's. We start with the transform of y and then we go to our function of y, our first derivative. If we had more terms, then it would be our second derivative, third derivative, and so on. So that's our first transform, and then it's 2 times the transform of y prime. So in this case, n is 1. So this is s to the first y, big Y of s, minus f of 0. So s to the first, no s's, y transformed, and then f, or not f, but y of 0. We don't have another term because this gets us down to no s's. We're not going to do negative s's, so there's no y prime here. And then when we simply transform y, that transforms to big Y of s. And on the other side, when we transform 0, it's still 0. So let's substitute in for our y sub 0 and y prime of 0. So we have s squared y of s minus s times y of 0 is 2, so minus 2s. Y prime is 4, minus 2 times s y of s, minus y of 0, which is 2, plus 5 times y of s. So some of our terms have y of s's in them, some don't. Let's go ahead and distribute here, and let's copy what we have. So that's going to make that a minus 2s y of s plus 4. So all the terms that have a y of s on them, we're going to leave those on the left. Everything that doesn't have a y of s, we're going to move to the other side. Notice that the negative 4 and the positive 4 cancel. So the only non-y term is this one. So to get it to the other side, we would add 2s to both sides. The remaining terms have a y in them, so we can factor out y of s. That's going to leave us s squared minus 2s plus 5 times y of s. So we've taken the transform of the differential equation, transformed each term using our Laplace transform. We want to solve this for y of s. So if we divide both sides by the parentheses, have to be very careful not to get our s's and our 5 mixed up. So big Y of S is 2S over S squared minus 2S plus 5. And that's important because if we have big Y of S, then to get Y, which is what we're looking for, we just do the inverse transform of that. And if we inverse transform the left, we inverse transform the right. So when we untransform Y of S, that gives us Y of T, which is what we're looking for. What function of Y satisfies this differential equation? So we just need to be able to transform the right. So in order to do that, let's pull the 2 out front. That leaves us S over that denominator, and that denominator needs to be, it doesn't factor, but we can complete the square. We want to write this as, if it's not able to be written as x squared plus b squared, as s minus a squared plus b squared. So in order to do that, we need to take the first two terms and add something to them that will make it a perfect square trinomial. So take half of this number and square it. So -1 squared is 1. So we're going to rewrite, or we're going to, let's say, add 1 to the first two terms, which means we also need to eventually take away 1. Notice we're just adding 0. That makes that part s minus 1 times s minus 1, or s minus 1 squared. 5 minus 1 is 4, which is 2 squared. Be careful that this is an s here. Notice 1 plus 5 is 6, minus 1 is 5. So this is equivalent to what our denominator was, but it just looks. So we have two formulas for our inverse transform. One of them is when we have a b on top, s minus a squared plus b squared on bottom. The other one is when we have s minus a over s minus a squared plus b squared. Now, if a is 0, then it could be just s over s squared plus b squared. So we have an s on top, and this is not just s squared, so these have to match. Since this is an s minus 1, we need an s minus 1 on top. But we can't just simply subtract 1, so we also have to add 1 to keep it equivalent. So let's don't forget our inverse Laplace symbol there. So we need to transform. We have a 2 out front. We have an s minus 1 over s minus 1 squared plus 2 squared. We don't need this plus 1, so let's put it in its own fraction. So let's put a plus 1 over that same denominator. Group that together, and then have that together. So that over our denominator plus that over the denominator. So that makes this s minus a over s minus a squared plus b squared. But if this is a constant, this has to match b. Well, b is 2, so we need a 2 here, which means we need to divide by 2 out front. So now this is b over s minus a squared plus b squared. So now we can transform that. Now we've made it fit one of our inverse Laplace transformation formulas. We have to be careful here. That 2 is times whatever that changes to. So I need a parenthesis around all of that. So 2 times whatever we change that to. So when we inverse Laplace that, that's e to the at, so e to the 1t times cosine bt. And here, this is e to the at, so e to the 1t sine bt, so sine 2t. And that has a 1/2 in front of it. We can distribute that 2. So y of t is 2 e to the t cosine 2t. 2 times 1/2 is going to make that 1 e to the t sine 2t. So that's our solution for our differential equation. Notice we didn't use any of the previous methods of solving differential equations. All we did was we transformed it into a function of s. We reorganized things, solved it for y of s, and then we untransformed it. We did the inverse transform to get it back to a function of t. So if we did everything correctly, this is the solution to our original differential equation. This is the function for y that will satisfy this given differential equation. That takes into account our initial conditions. Notice there are no arbitrary constants in that particular function. Now the next one that we're going to take a look at is not homogeneous. We have a function on the right side, but we are going to treat it the same way. We're going to take the Laplace of the left side and the Laplace of the right side. So we need to transform y double prime minus 4 times the transform of y prime plus 5 times the transform of y, and that will equal 4 times the transform of e to the 3t. Remember, with coefficients, we can pull our coefficients out front. So as we did on the previous problem, when we transformed y double prime, this is our second derivative. So using our formula, it's s squared big Y of s minus s to the 1 less power y of 0 s to the 1 less than that power y prime of 0. So that's our first term. And then it's minus 4 times the transform of y prime. There is a formula for translating or transforming y prime, or you could use the general form with n equal 1. Either way, we're going to get s to the first y of s minus y of 0. And then when we transform just y, the transform of y of t, that transforms into y of s. We don't know what function y is, so we don't know how other way to express that transformation other than we're transforming y of t into y of s. Now on the right side, 4 is a coefficient, and when we transform e to the 3t, that's 1 over s minus a, so s minus 3. Or we could call that 4 over s minus 3. All right, let's substitute in our initial values. So we have s squared y minus s times y of 0, so s times 2, minus our y prime of 0, and then 4 times s times y minus 2 plus 5y of s equals 4 over s minus 3. So let's get rid of these parentheses here. That's going to make this a minus 4s times y minus 4 times minus 2. That's going to make that a plus 8. So let's collect like terms, and then everything that doesn't have a y of s, move it to the right side. So we have a y squared that has a y of s. We have a minus 4s that has a y of s. And we have a plus 5 y of s. So that takes care of those. And then we have a minus 2s, and negative 7 plus 8 make 1. So the terms that don't have a y of s are these two. So add 2s to both sides and subtract 1 from both sides. So those will cancel, and that's going to leave us 4 over s minus 3 plus 2s minus 1 on the right. On the other side, we have s squared minus 4s plus 5 that are all being multiplied times y of s. So to get y of s, we can divide both sides by that parenthesis. So those will cancel. So that gives us y of s equals If we divide the first term by that, we're going to get 4 over s minus 3 times s squared minus 4s plus 5, plus the next term divided by s squared minus 4s plus 5 minus 1 over s squared minus 4s plus 5. We're eventually going to do partial fraction decomposition to break this apart. But before we do, let's combine all of this under a common denominator so that we don't end up with replicated terms or fractions, 2 or 3 different fractions with the same denominators. So our common denominator is going to be s minus 3 times s squared minus 4s plus 5. So the first fraction has all of that already on bottom. So it doesn't need to pick up anything else. The second fraction has the quadratic factor, but it doesn't have an s minus 3. So we need to pick up an s minus 3 on top and bottom for that fraction. And the last fraction, it needs to pick up an s minus 3 as well. So we had 4 over that. We originally had just 2s over that, but that term picked up an s minus 3 on top and bottom. And the last term already had that, but it picked up an s minus 3 on top and bottom. So y of s with a common denominator of s minus 3, s squared minus 4s plus 5. If we look at the top, we're going to have a 2s squared there. We're going to have a minus 6s, and a minus 1s, so minus 7s. We're going to have a 4 here, and we're going to have a plus 3 there, so plus 7. So when we combine that into a single fraction, then we end up with that. Now we would want to do partial fraction decomposition to split this up into something over s minus 3 and then something over s squared minus 4s plus 5. Now, for time's sake, I'm going to let the computer do that. So that's going to give us a 2 over s minus 3, a 1 over s squared minus 4s plus 5. So we would just need to go in and we would need to transform each of these to get back to y. We would need to do the inverse Laplace of the left side, and that's going to give us y of t, which is what we're looking for. So to find out what that is, we just need the inverse transform of each of these terms. We have 2 terms, so inverse Laplace each of those terms. The first term, we could take the 2 out front, and that would be just 1 over s minus 3. So when we have 1 over s minus a number, that's a, and that inverse Laplace is into e to the at, so e to the 3t. This one we did one like this on the previous problem, but I'm just going to work through this again just as a reminder. When we have a quadratic on bottom, we need that either as s squared plus b squared or s minus a squared plus b squared. So we have an s squared and an s term, which means we need to complete the square for those 2 terms to make that into s minus a times s minus a. So actually I think we had different numbers on the previous one. I was mistaken. What did we have? We had s squared minus 2s instead of s squared minus 4s. So to complete the square here, if we've got s squared minus 4s plus 5, then we need to take half of 4. Half of 4 is negative 2. Square it, that'll make positive 4. And then we have a 5 over here. If we add 4 here, we have to subtract 4. So that gives us a net of 1 here. Notice 4 plus 1 is 5, which is how much we had to begin with. So this first one factors to s minus 2 squared, and then that's just 1 squared. So we can rewrite that as, we have a 1 on top right now. That denominator can be written as s minus 2 squared plus 1. Okay, so since we have a constant on top and not an s, then that constant, if this is b squared, that just needs to be b. So that's what we have. We have s minus a squared plus b squared on bottom, and we have that same constant that's being squared on top. So we can do the inverse Laplace there, bring our other terms down, and when we do the inverse Laplace there, we get e to the at times sine of b, which is 1, t.